Hi class, we're going to be covering chapter 19, 19.1 and 19.2. My voice is not completely back, so it may sound weird at times. So this is spontaneous and non-spontaneous processes. So what is spontaneous? When you look at a chemical equation, we just naturally assume that it goes. But in reality, when you're learning chemistry, there's a lot of reactions that don't go, or they don't go very well. And you're learning this with equilibrium, and some just they don't go in that direction, but we don't talk about that. So this is a point where we're going to talk about why some reactions happen spontaneously and why some do not. So when you look at a chemical reaction, why do some naturally just go in that particular direction? So this is similar to a rock on the top of a hill. If it rolls down, it'll roll down on its own spontaneously. Nothing can, if it's just at the top of it, it will go. It's not going to just randomly stop. But a rock that's at the bottom of the hill will never just spontaneously go uphill. You can move that rock uphill, but you'll need an external force, something to push it up the hill. And that's the difference between spontaneous and non-spontaneous. So a spontaneous process is a physical or chemical change that occurs by itself without any external force or something helping it along. It does not require it, and it will keep going until it reaches equilibrium. So for instance, heat will naturally always flow from something hot to something cold. It will never go the opposite way. So if the process was to go in the opposite direction, then that would mean it's non-spontaneous process. So for instance, the rock going downhill is spontaneous, but the rock going uphill is a non-spontaneous process. It can still be done, but it's a non-spontaneous process. So here is an example of some spontaneous process. A waterfall runs downhill. It'll never go uphill without some kind of help. A lump of sugar will dissolve in coffee. It will never just stay intact. At 1 atm pressure, water freezes below zero, and above zero, it melts. Heat flows from a hotter object to a colder object, and gas expands in evacuated bulbs. So that means that it will, when given opportunity, it will expand until it hits resistance. And iron exposed to oxygen and water will form rust. So a nail left out in the environment is prone to rust because it's dealing with water, vapor, and rain, and so forth. So again, if you look at a picture here, this is spontaneous going down the hill, and it's non-spontaneous up a hill. And if anybody's ever walked up hills or hiked, you definitely know that. So the first law of thermodynamics is about energy, conservation of energy. It will not tell you anything about spontaneity at all. It's just, this keeps track of energy and the forms of energy. Remember, energy is neither created nor destroyed. So it keeps track of energy and how it can transfer from one from another. But it will not tell you anything else about whether reaction is going to go in the forward direction or is actually spontaneous in the opposite direction. Okay, so chemical thermodynamics is a study of heat and work. This is more just a review. Heat and work involved in chemical reactions and the physical changes such as a change of state. So we're going to be looking again at spontaneous and non-spontaneous, but it does involve, we're going to discuss enthalpy, and we're going to bring in something called Gibbs free energy and so forth. So chemical thermodynamics is the study of heat, and heat is going to be involved in some of these reactions that we're going to look at. So a spontaneous process happens under indicated conditions. So for instance, temperature and pressure. Different temperature and pressures, we can get changed phases of changing. So we're going to have to look at some variables as well. The process of understudy is the system. Remember, the system is the reaction or the experiment, and everything else is surroundings. So we put together the system plus the surroundings, and that makes up the universe. And we're going to consider these definitions here. So if you need to make sure you are very comfortable understanding what the system is, what the surroundings are, and that those together make up the universe. In a reversible reaction, the enthalpy change, remember enthalpy is heat. If it's at constant pressure, it's just the heat flow. And if it's not at constant pressure, it's also work that is involved. Remember the W? And the W is made up of pressure with change of volume. Excuse me. The enthalpy change of the forward process is equal in magnitude, but has the opposite sign in the enthalpy change. What this means is that the value of it going forward, if it's in a reversible reaction, it will be that same value. That's what magnitude means, but with a negative sign showing it's going in the reverse direction. So let's cover what spontaneous means. Spontaneous reactions can be exothermic. They can be endothermic. The first law does not determine if it's spontaneous, meaning it'll naturally just occur. This is where a new quantity comes in, which is entropy, and it's defined with an S. It is a thermodynamic quantity that is a measure of how dispersed the energy of a system is among different possible ways the system can contain energy. What does that mean? It simply means that we are looking at the energy that is being involved in this experiment or reaction. Now, entropy is not energy. It is the dispersal of this energy. How dispersed does this energy that we're dealing with in this part of the system, how dispersed, how spread out is it? Is it dispersed and spread out at all? Or is it actually staying concentrated? So entropy is disorder, or dispersal is an easier way, but it's not the actual energy itself. We're taking that energy and we're looking to see what happens with it. Excuse me. And how many different ways can that energy be spread out? That's the states that we're going to talk about in a little bit. Entropy of the system plus the surroundings increases the spontaneous process. Because if there's entropy in one part, if it goes into the other part, meaning the surroundings, we have now increased disorder in both the surroundings and the system. So entropy is a state function, which means it doesn't care about how it got from point A to point B, just that it went from point A to point B. So that's where we only look at initial and final. Depends on variables, temperature and pressure. That determine the state of the substance, because you can have different temperatures and pressures, and that will determine which physical state you're looking at on some substances. Entropy is an extensive property. It means it depends on the amount of the substance present. It's measured in units of joules per Kelvin, and that's where that word absolute will come in. Absolute simply means it's referring to Kelvin. And entropy change is calculated from delta S, which is entropy final minus entropy initial, which is very which is very similar to how we've determined enthalpies of reactions. Okay, so the second law of thermodynamics, the total entropy of a system and its surroundings always increases for a spontaneous reaction. So that means that we will always have more disorder, not less. Entropy, again, is a measure of how energy has been dispersed. It's not the measure of energy itself. We're looking if this energy stayed concentrated or did it spread out as much as possible. In a spontaneous process, there's always an increase in the entropy of the universe. So that means that the system and surroundings, the total has to equal an increase in the universe, which doesn't always happen with what we're going to look at as this chapter goes on. The total energy of the universe is constant, but the entropy is increasing. So first law talks about energy being constant. We cannot create nor destroy energy. We can't just randomly make it up. It keeps track of that. But the entropy will always decrease when we're dealing with energy if it's a spontaneous reaction. So which process is inconsistent with the second law of thermodynamics? A, the spontaneous creation of energy from nothing. I just spoke, and that doesn't happen. That's the first law. Spontaneous creation of matter from nothing. Nope, not that either. The spontaneous concentration of energy from dispersed energy. Yes, we are looking at if a spontaneous reaction happens, we take concentrated energy and it gets dispersed into greater, it's still the same amount of energy, but it gets dispersed into as far as it can to cause into the universe. Okay, so for example, the melting of ice from a solid to a liquid is endothermic and spontaneous at temperatures above the melting point. That's a spontaneous reaction. So if you have ice and it's above zero, it's going to melt. Even though it's an endothermic reaction, it will melt. However, the freezing of water is exothermic and spontaneous below. So anything below zero, that water is going to freeze. And even though it's an exothermic, it's still a spontaneous. So depending on what temperature the water is at, will tell you whether it is going to spontaneously occur and be exothermic or spontaneously occur and be endothermic. Some reactions only occur spontaneously in one direction and can't go in the other. For instance, the combustion of gasoline, by providing a spark, you produce carbon dioxide and water. But we can't go back and create or do a reverse reaction with gasoline combustion because it's not spontaneous and it can't occur. So not all of these can go back into another reaction, such as water. Graphite is more stable than diamond. So the conversion of diamond to graphite is spontaneous. So what's actually occurring is diamond will eventually convert to graphite. But this is a very slow process. Remember, chemistry is all about the lowest stable energy. And if graphite is more stable, then that's where it's going to go. But it doesn't occur instant. So spontaneous, yes, it is a spontaneous reaction. However, it does not determine the speed of a reaction. So this is going to take a very long time, not even in our lifetime. So this is a good example to have you understand that we're dealing with a spontaneous reaction occurring, but not the speed or rate of it. The speed or rate has nothing to do with spontaneous reaction. We just know whether it's going to happen naturally or not, but we don't know the speed of how long that's going to take. And speed has to do with kinetics. So if we look here, kinetics has to do with immediate steps and speed and activation energies. We are interested, remember, entropy is a state function. We only care about final and initial. So when we look at something like this, we only care about what was in the reactions, initial, and the final states to determine spontaneity. We're really not trying to involve ourselves with the kinetics at all. We cannot determine how fast a reaction occurs. We can just determine entropy. That's it.